So the sleep has an important. Oops. Oh, okay. Sleep has an important role to support our visual system, especially the visual perceptual learning. That is the facilitation of sensitivity by repeated visual training. It is known to be enhanced after sleep. So one fMRI study conducted by Yotsumoto revealed that after visual training, the signal enhancement was observed specifically on the trained location of the primary visual cortex during sleep. So it possibly reflects the stabilization process of the visual learning that is called consolidation. Okay. So our visual perception has known to be influenced by this tactile sensation as a cross-motor interaction. And for example, the visual tactile motion direction are congruent, and the visual motion sensitivity is improved. And on the contrary, when visual and the tactile stimulation are presented with a delay, the repetitive tactile motion stimulation inducing this visual motion after effect afterwards. And the presumed neural mechanism for such a cross-motor interactions, the attributes to this are the partially overlap the neural circuit. For example, the fMRI study revealed that the human middle temporal complex activation, not only visual motion processing, but also the tactile motion processing. So these results indicate that the tactile sensory input can influence the process of both facilitation and adaptation in the visual tactile interaction. So based on these evidences, we constructing a hypothesis that the tactile motion stimulation during sleep could facilitate subsequent visual motion sensitivity in a directional selective manner, either in the direction of the presented tactile stimulation or the opposite direction due to the adaptation. To test our hypothesis, we designed the sleep experiment with the different conditions. To check the change of the visual motion sensitivity across sleep, we assigned the participant a random dot motion task in the morning and afternoon. And in this task, the participant required to detecting one of the 8 possible motion direction, coherent motion direction from the randomly moving dot that is presented on this computer screen. And it's a change of visual motion sensitivity before from the morning to the afternoon. It is the use for this effect of our primary interest. And between this visual motion random dot motion task, and we also setting 3 different conditions. And in the sleep motion conditions, participants receiving linear tactile motion stimulation at the specific direction, either the up direction and up direction, down direction, left direction, and the right direction on the index finger. And this stimulation is presented during slow wave activities, mainly in this stage 3 of the non-rapid eye movement sleep. And the sleep random condition and the experimental setting up is exactly the same as the sleep motion condition, but the participant receives random tactile stimulation. And as you can expect, that the sleep motion condition is the participant receives the tactile motion stimulation during wakefulness. And to present the tactile stimulation to the participant during a slow wave sleep, we creating the automatic system to detecting slow wave activities and present the tactile stimulation in the real time. And in the system, the frontal EEG was converted to the frequency spectrum, and then this data was checked for motion, checked by 2 support vector machine for the motion artifact and the slow wave activities. And then the stimulation was presented during the slow wave activities following to this stimulation criteria. And here's the result of the visual motion sensitivity changed across sleep and wake state. And this result is based on this perspective that the visual motion coordination is congruent with the tactile motion condition based on the hand reference frame. And behavior results show that in the sleep motion conditions, significant improvements occurred only in the direction opposite to the tactile motion stimulation. And on the contrary, no improvement occurred in the wake motion condition. So it demonstrates that the visual motion sensitivity is facilitated in the tactile directional selective manner due to the possible motion adaptation. And also this improvement is also correlated with the number of the slow wave activities per minute, mainly on the actual over the possible location of the somatosensory area. So it suggests that the slow wave activities over the somatosensory area providing the certain state for the neural adaptation that could be inducing a bias effect on the ongoing consolidation process of the visual perceptual learning. And we also performed the time frequency analysis of the sleep EEG data to compare the effect of the tactile motion stimulation and that of the random stimulation during the sleep. It revealed that the tactile motion stimulation inducing this higher power at this the high beta frequency on the external over the occipital region. So it suggests that the visual motion can process or tactile motion information even during sleep. Okay, so I move to this, the result of our second experiment. The recent study suggests that the tactile spatial information is a result of this integration of the information across the multiple reference frame, such as the hand, head, and the visual-based reference frames. And it's also the tact context may affect this spatial processing via top-down signal. The improvement of the visual motion sensitivity that I presented in the previous two slides implicated that the hand reference frame is a dominant role to determine the tactile motion direction. However, it is still unknown which reference is used to judge the motion direction during the sleep when the misalignment that happens across different multiple reference frame. So to investigate it, we conducting this second experiment that dissociates the hand and head reference frame by manipulating arm posture. So in this experiment, we inducing the tactile linear motion stimulation from the bottom row to the top row on the index finger in the new participant whose right arm stretched out 90 degrees to the side. So in these conditions, the tactile direction can be interpret as the up direction and from the hand reference frame or the right direction from the head reference frame. And here's the result that visual motion sensitivity was improved only at the direction based on this orientation of the hand reference frame. So our sleeping brain anchors the hand reference frame for the visual tactile cross-motor interaction during the sleep, regardless of the location of the arm location of the arm posture. And I also examined the effects of arm posture changed. I performed this time frequency analysis of the sleep EEG data during this motion stimulation in the experiment 1 and 2. And the result revealed that we found that higher frequency at the beta, higher power at the beta frequency and mainly on the frontal extrode when the participant changing the posture. So we think that these results may reflect the selection process of the body reference for the visual tactile interaction during sleep. Okay, so here's the conclusion. The tactile motion stimulation on the fingertip during the slow wave activities selectively enhance the subsequent waking visual motion perception based on the hand reference frame. And also to show that the repetitive tactile motion information during sleep lead to the directional selective invariance in the visual motion processing, which results in this biasing ongoing consolidation process of the visual perceptual learning. That's an acknowledgement, and so I really thanks to the people who contribute to the project. I also present these results in this afternoon's poster session, so that I really appreciate if you have any comments or feedback, and please come to my poster. Thank you very much for your attention.